Okay, we have a tangent plane equation. And I think I mentioned that this is sometimes called the linear approximation. Whoops. So the idea here is that if we have a function that's not a plane, some curved function, the idea is to use the plane as an approximation to the function near the point. So let's see if we could draw a picture here. Say this is just a piece of the function. And we have this point. And then we get the tangent plane. The idea is that if we have another point on the plane or a point on the surface, put that point over here just to let you know that it's on the surface, and then there's a corresponding point on the plane that has a little bit of a distance between them, but we can still get a pretty good approximation to that point. The tangent plane and the linear approximation. Yes. So the tangent plane is the linear approximation. If you look at it, it's the exact same right-hand side, except we're calling it slightly different things. Yeah.
So linear approximation and the tangent plane are the same?
Yes. Yeah.
So on this, are we going to be using the term parametric?
Yes. The book does, and so I think I can also. So, see if we can find an example. I was trying to look at the problems in your homework to see if there's a good example for this. Verify. Yeah, but there's no approximation part there. Let's try number 7. We haven't talked about dz, but let's change the question a little bit. But we'll use the same functions. So let's say approximate f of 0.95 comma 1.9. And what we want to do is we want to, first of all, have nicer numbers instead of these decimals that they throw at us. And what we want to do with those nice numbers is we want to use those nice numbers as like the point, the base of your tangent plane. So if we take a look at this 0.95 and 1.9, they're fairly close to 1 and 2. Would you agree that that's the case? 0.95 is like 0.05 close to 1, and then 1.9 is like 0.1 close to 2. So we can use this function and find the tangent plane at this point 1, 2, and then from there move a little bit off to see what the approximation might look like. So let's come up with our tangent plane, which is going to be our linear approximation. What do we need? We need a function evaluated at 1, 2. We need the derivative of the function evaluated at 1, 2. And then we're going to multiply that by x minus 1. And then we need the function evaluated, the derivative with respect to y evaluated at 1, 2. Color here. So we need those pieces. Let's find them. Let's find f of 1, 2. That's putting 1 in for x and 2 in for y. So 13, is that right? 9 plus 4, 13. Let's find the derivative, and then we'll put in 1, 2. So derivative with respect to x is 18. X plus 0. Eventually I'll stop putting plus 0. But I'll do that a little bit longer just to have you guys remember that the derivative of constant is 0 and y is a constant with respect to x. So we need to put in 1, 2. In this case, there's only an x, so that's just 18. Fy is the derivative with respect to y. Guess I should put 0 here still. Fy at 1, 2, put in 1 in for x and 2 in for y, and so there he goes. Our linear approximation then is equal to 13 plus 18 times x minus 1 plus 4 times y minus 2. So now that we have that, our function evaluated at 0.95, 1.9 will be approximately equal to this linearization evaluated at 0.95 and 1.9. And then what we have, or what we could do, is put in 0.95 and the 1.9 where x and y are. So this is what, at negative 0.05, and this is negative 0.1. Now we'll need a calculator. What is it? 12.5. Okay. Now this is especially useful if you don't have a calculator. Because putting numbers into a linear function has been a lot easier than putting numbers into a function where you have to do weird stuff with the x's and the y's. So, yeah.
Is it plus 4 instead of negative 4?
Oh, yeah. Thanks. Is it? Now we need to fix that. Still 12.5? What is it? 11.7. Yeah, so the idea is that if we had some funky looking function with maybe trig or ln's or exponential functions, putting an x and a y into a function like that would be kind of difficult, whereas putting an x and a y into a function like this, a linear function, is a lot easier. So that's a general idea behind this approximation. We can double check to make sure that this is actually correct. Let's actually put x equals 0.95 and y equals 1.9 into the original function and tell me what you get. Can somebody do that, please? So you see that you get 11.7325 is what you would get if you put it into the original function, and we got 11.7, which is close. So we got a pretty good approximation for that. We're off by that little bit of error. Yeah?
Some way to account for that error? Like later on first?
Probably. How about like right now? So let's take a look at those functions or these formulas. And let's get introduced to what we call the differential. Tell me about these two formulas here. One of them is the linear approximation that we just saw. The other one is a differential. What do we have here? What are similar? What are different? Go ahead, Matt.
It looks kind of similar in that there's like x minus a kind of represents a change in something,
Mm-hmm.
and which is very similar to the idea of dx and dy, a change in a function with respect to x.
So there's a dx, dy, or the dx and the dy separately, and they do represent a little bit of a change. And sometimes people even call this delta x as how the change happens from a particular value, a, and delta y would be like how the change happens from a particular set value, b. Now there's another difference between these two equations. You're missing like a starting point function here that gives you a base to where you start off. So let me attempt to draw that picture again, and this is kind of like the picture that they have in the book, I think. Maybe a different book, I don't know. I think it's this book. So we have the surface, z is equal to f of xy, and we have the plane, z is equal to L of xy, which is our linear approximation. Maybe if we dot this, see that this is kind of behind. And what's happening is that we're seeing some stuff down on the ground, your domain. AB. So pretend that AB is on the XY plane. In fact, we can even draw, might as well draw the whole thing, right? So we have a point on the plane, a point on the domain AB, and then we have a point on the surface A, comma B, comma f of AB. And the important part about this point, well, they're all important, but the important part about this point is that you have a z value of f of AB. So that's f of AB, kind of gets you there. So if you go a little bit off of AB, this point in the domain that's a little bit off of AB is going to hit the surface and will hit the plane. So these are the two dots in the previous picture that we saw. One of them is on the surface, and then the other one is on the plane. So let's call this point CD, I don't know. So the idea is that you're sitting at the point AB and then you move to a different point CD. So what we're going to account for is a movement in the X and a movement in the Y, which we'll call delta X and delta Y. And what happens is that these movements are in the differential, or sometimes denoted as dx and dy. And so what's important is here is that there's also a change in the z. So the z is going to change from one point to the other. And a lot of times they call the delta z, well, how should we put it? Well, let's put it this way. The dz is the change. Well, I guess they have it here. The dz is this change that describes where you are on the plane. Whereas the delta z, so this is your z value, on the plane. Whereas your delta z let me put it this way again. Your f of CD is equal to f of AB plus delta z.
That term didn't disappear, just moved to the other side.
Kind of. The f of AB, yeah. Oh, wait a minute. Ernst?
So dz represents a change in the linear approximation, and delta z represents a change in the actual function.
Yeah, that's it. Thanks. Yeah, so I think I needed to add something here, so let me add it over here. F of CD is approximately equal to f of AB plus dz. So this here wasn't quite correct. I needed to add the offset over here, which gives the height. So f of AB. I'll put it over here. F of AB plus dz. All right. So what Harrison said. This is the plane, or this is the value of the function, and this is the value of the plane. All right, so the summary was that the delta z is the change in the function. The dz is the change in the plane. The change of height in the plane. And what f of AB gets us is that it gets us to the starting point. F of AB gets us to the starting point. And then now this little change in the function versus the change in the plane is the difference between the delta z and the dz. Does that make sense? I actually want to take this just a step further and take a look at these two, because the problem that we didn't quite do exactly according to the instructions was finding the delta z and the dz. So if the delta z is just a change in the function from AB to CD, then this is going to equal to f of CD minus f of AB. And this is the original point. On the other hand, dz is going to be equal to, if we bring this over to the other side, since this is an approximation, we're going to use a tangent plane. So the tangent plane, I'm going to write this over again, f of AB minus fx AB x minus a plus, this is a plus, I'm sorry, plus fy ab y minus b. So that's this approximation, and then you're going to say minus this thing that you would bring over to the other side, f of ab. And then you would get pretty much that formula for the differential, because these two would cancel, and then you just have this stuff. Okay. So to figure out dz from this approximation, the value on the plane, we're kind of changing the f of CD and using the approximation for that. And then this is actually C minus A and D minus B, which changes into your dx and your dy. Okay? Hopefully this will give you enough tools to be able to tackle this homework set. Now, there was another interesting problem that I saw, and for now, let's use implicit differentiation to try to solve for this, and then later on we'll see that we're going to find something more interesting to solve for a problem like this. So find an equation. Maybe I'll type this up. No, maybe I'll write it. Equation of tangent plane to the sphere, x squared plus y squared plus z squared is equal to 1. At the point 0, 0, 1, and at the point 1 over root 2, comma 0, comma 1 over root 2. So based on the equation of the plane that we had, all we have to do is find the derivative with respect to x and the derivative with respect to y. That's if we had a function, f of x, y. So unfortunately, we don't have that scenario. Right? So we need fx and fy, but we don't have a z is equal to. Oh, yeah, I suppose we can solve for z is equal to this stuff, and then we'll have square roots and stuff. So is there a way to get around that? Instead of solving for z and then taking derivatives, now I have to deal with square roots and stuff like that. Instead of doing that, can I do a workaround?
I'm assuming yes.
Okay, so the question is, what technique have we kind of learned briefly that might help us with this? Yeah, thank you. So if we do an implicit differentiation, this would be easier, I think. You guys remember taking implicit differentiation? Kind of. Let's find fx. So we want to take the derivative of this thing with respect to x. Actually, we'll probably end up calling it zx. So if we take the derivative of this thing with respect to x, we're going to get 2x plus 0 plus, remember how to take the derivative implicitly, you have to do like a chain rule, so it's 2z times the derivative of z with respect to x, I'll call it zx. And then the derivative of 1, remember, it's not 1, it's 0. So we take, we solve for zx, we're going to get negative x over y, or x over z, because they'll be negative and the 2's will cancel. So now that was a lot easier than taking the derivative of square root. I mean, which we could do easily, but now we got something that was a little bit easier. Yeah, that's what I'm saying, is that this, 1/2, this thing raised to the negative 1/2. And, all right, so fy, if we go through similarly, we're going to get 0 plus 2y plus 2z times the derivative of z with respect to y. And then solve for the derivative of z with respect to y, and then you get negative y over z. So here we have the derivatives that we want will work as our fx and fy, but remember that formula kind of looks like this. I don't know if we use z or lx or something. Let's use z is equal to f of ab plus fx of ab, comma, not comma, x minus a plus fy of ab, y minus b. So let's see how our pieces of information will fit in. This is not exactly the formula that we use for this, but it is, it'll kind of model what it is we're looking at. There's things here where if this fx is equal to zx, then I just have to work that out and put in appropriate values, and then I can get what I want. So if this is our formula, how are we going to fill this fx of ab, since zx is actually a function of x and y and z? Let's find a... Actually, I don't want to do this. Let's just do this one. Let's find the equation of the tangent plane to this graph right here. So what's my fx going to be? And I'll put fx in quotes here. So one of the things that you notice that in a lot of cases, you're usually just given the a and b values, and then you have to find the c value or the z component. But in this case, you're given the whole three-dimensional point. So what happens here? What's this equal to? Negative, what's x equal to? 1 over root 2. And we don't have a y, instead we have a z, but fortunately z is given over here, so we'll just put that in as well. So this is your x value, and this is your z value. And then that's just negative 1. Does that make sense? And then similarly, to get your fy, your y value is what? What? 0. And then 1 over root 2 is your z value again. So this whole thing is just going to equal to 0. So that's taken care of. What is this? Do you remember where f of AB came from? Yeah? Do we plug in the three values in here? If we do, we're going to get 1 is equal to 1. That's not really... Why? So this f of AB, remember, is a z value of the point. Right? So that's just 1 over root 2. So then the equation of a plane is going to be z is equal to 1 over root 2 minus 1 times x minus a plus 0 times whatever else is left there, because so if you were to graph the sphere, the unit sphere, and then graph this, you'll see that it'll actually be tangent. Okay? Should we see the graph? Or are we all good? So the plane is z is equal to 1 over square root of 2 minus 1 times x minus 1 over square root of 2. That looks pretty tangent. Okay? Take a picture.
Effectively, you're integrating, aren't you?
No? No, I don't think so. All right. Okay, think about it and then we'll talk. Okay, so this is the tangent planes. We'll see later on that we're going to have a nicer way to attack this that's kind of similar to this, but we won't necessarily call it implicit differentiation. In fact, it becomes a more powerful tool, and it becomes a more it's a deeper theory into derivatives, and so it'll be fun. All right, let's go to the next section, and our next section is chain rule. Now, the book starts off with a special case of the chain rule, and so let's take a look at that. What's the special case look like? I think it looks something like this. What do we use a chain rule for? Derivative of what? Of what? Nested? Composite? So composite functions, right? So the chain rule is used for taking derivatives of composite functions. So we compose functions back in pre-calculus. We have FOG. Remember that? Fog. Which is really saying you take the G function and then you put it inside of the F function, and then when you take the derivative, you take the derivative of the outside and then to take the derivative of the inside. So how does that play into the chain rule in 3 dimensions? So let's see if we can find a composite. And so the idea of a composite is kind of complicated to think about. Well, except there is a special case where if we have a function that goes from R2 to R, so you can write it as z is equal to f of xy. And then let's say we had another function, and I'll call it R, and you'll see why I call it R, that goes from R to R2. Goes from a real number to a pair. How might this function look like? No, that would be something like this with an x and a y. No. Now here's my hint. The input is one, let me call it a parameter. The input is a scalar, a number. So R of just one variable, and it's a parameter. So what would be a good, no? A parametric vector. So what did we usually use for that, RT? We usually use T. And then our output now is going to be a vector. Now we can just say x of t, y of t. Put in your favorite function, sines, cosines, whatever. So if we compose these functions, we would compose it as putting the r of t into the function. So I'll write z is equal to f of r of t, kind of like this composition of FOG. Now, let's imagine how this is going to look like. Z is equal to f of xy. Tell me about R of t. Where does it live? How might it look like? Any ideas? Yeah?
I'm just gonna take a guess here.
Yeah, make a guess.
It's gonna track all the points. That R of t is going to track all of the points on the plane from relative to some point. Like some point like on the x on the physical.
On this graph or on the
Like on the bottom.
on the bottom? Okay.
I guess in this case,
Yeah, so
all the points on the plane.
so you're getting a little bit ahead of my question, but my initial question is, what's R of t look like? And I guess it doesn't have to be a closed. So R of t would be something on the xy plane. Would be on the domain of our function. And now, I think what Matt was talking about is that if you were to trace out what this is going to make by projecting it up onto the surface, that's what this function is doing. Okay, so R of t is on the domain on the xyz. And then your z values are going to be given by this. So saying that if you take a point here, let's take a random point. Say when t is equal to t1, we put that into the function. R of t1 is going to equal to x of t1, comma y of t1, which will, let's just call it a and b. Essentially a point. Maybe I should use parentheses. And now I get to put this point AB into the function, and that's going to give me the height. I can kind of backtrack the work here. F of AB is actually equal to F of R of T1, specific point T1. Okay. So what I have here is a composition, F composed with R, goes from, well, R is the inside function, and it starts with a t value. Right? And then it goes into a two-dimensional domain, and then it comes back to a regular R value, which is Z. So essentially, if we eliminate the middleman, this really is a function from R to R, which is a function that we know of from calculus, Calc 1, pre-calculus. Okay? Is the setup okay so far? Does the picture make sense? You got something on the xy plane, and you have a surface, and then you're projecting whatever it is, the path that you're drawing on the xy plane, you're projecting it up onto the surface. And the surface has the point that the new path on the surface follows has an x and a y and a z value. And this is the z value of that path. It's the z value of the new path that has been projected up on the surface. So it's controlled by the x and the y in the domain and the curve, and then the z of the function. So we might be interested in finding the rate of change of the z values as you move along that path. Okay? All right. So, where are we going with this again? Tangent plane, chain rule. No, not tangent plane, just the chain rule. Should we keep going with the derivative of this, or should we try to get an example? Are you guys okay following formulas, or should we cut to an example real quick and then come back? Example?
Same dz for rotating.
No, not quite. It would be dz dt.
Okay, because we have parameters.
Right.
And then does that, where does the parameters and the
We'll see. We'll see when we take the derivative. All right. Let's put this in an actual context of an example. Let's say let's put ourselves in a mountain. So this is your function. And let's say on the map, you're trying to follow a path on the map. So your map is two-dimensional. And you're trying to follow a path. Let's say the path is going at some diagonal, maybe. Or maybe parabolic. So if you take a look at these two things separately, it's my saddle. All right, let's actually draw a saddle. I don't know how to draw a saddle. Ooh, that's pretty good. Dang, that's good. Okay, I got me a saddle. It's been hoisted up 5 units, so just draw it a little bit above. And then here, if I were to draw this out from minus infinity to infinity, it would be your y is equal to x squared parabola. Okay? But it doesn't do us any good to keep it separate, so we can put it together. And there's a couple of ways to put this together. Well, let's see, graphically. I think I drew my saddle kind of backwards. Yeah. So let me draw it again over here. So I'd say this is how my saddle looks like, and my graph over here looks like this. So if you're drawing that up here, up on top, you're kind of going down, and then you're going to go something like that. All right, so we can do the composition, F composed with R of t. Now, if we physically do the composition and actually combine it the way we would have combined it earlier, you really just put the x in for the x, the y in for the y, and then you'll have your function, your new function. And you'll see that your new function is just a function of t. So the t that goes in for the x is t, or the function that goes in for the x is t. The function that goes in for the y is t squared. And so really, you have t squared minus t to the fourth plus 5. And now you see that this is really a function of just one variable t, and well, yeah, let's just call that g of t for now. And then this gives you the height of the function. What that means is that this curve can be expressed as the same x and y value, but if I kept it at 0, then it would just be on the xy plane. And then if I changed it to be on the surface, I would have to put in this function on the surface as a z component. So this would be t squared minus 4t, or t to the fourth, plus 5. Okay? All right, let's take a look at that in a graph. So I have z is equal to x squared minus y squared plus 5. So that's my saddle. I have a curve, and for me to be able to draw this, I'm just going to set up my curve as if it was in 3 dimensions, and then I'll just put 0 in for the z component. What's this? T squared, and 0. So you see that? That's on the floor. Now I'm going to draw another curve. But this time this curve is going to be actually on the surface. So it'll be t squared, what is it, minus? T to the 4th plus 5. So you see that that curve is actually on the surface. Why is it like that? So the curve is actually on the surface. And it's, if we look at it directly from the top, we'll see that it has that as its shadow on the xy plane. And if we look at it a little bit more carefully, in fact, if we take the surface out, see how it curves, and it curves in the z according to where its place is on the surface. It's just a projection of that onto, well, technically we're projecting it from the xy plane up to the surface. So that's how the picture is going to look like. So what do we want to do with it? Well, we're going to want to find out how it's changing in height. So this is your curve, but we want to find rate of change in height. We'll call it a z is equal to f composed with r as a function of t. So there's a couple things to note. We want to do a chain rule. Actually, let me rewrite this as f of r of t. And what we want to do is we want to take the derivative with respect to time, d dt. Now, one thing to note is that this is a straight d, not a partial of d, because the partial d says that this is a function of more than one variable. Now, granted, f is a function of two variables, but this whole thing is really a function of one variable, t. And as we do more examples, we'll see that come out clearer when you use a straight d and when you use a partial d. And so let me tell you the solution for this. This is actually going to be equal to the partial of f with respect to x times the partial of x, not the partial, the derivative of x with respect to t, plus the partial of f with respect to x, with respect to y, times the derivative of y with respect to t. And this is a weird formula, and it's very similar to the chain rule that you learned back in Calc 1, but because of the partial derivatives, there's going to be some other stuff involved. So next time we're going to dive deep into this, and then we'll find a solution for our derivative of that example that we came up with. Okay?
So, what I meant earlier was that